Hi, everybody. This is Miss PG from WCA Biology. Biology. This is kind of a weird video because I'm just going to be writing on a notebook here for you, but I just wanted to do a little bit of an review of like the first section in your Unit 1 for Biology. I know we don't have any live lessons yet because we're doing welcome calls and stuff like that. But I just wanted to make sure you don't feel, super lost. So I'm going to do a little review. The first part of this unit is kind of a review of chemistry, just a little chemistry stuff that you should have had in physical science. But if you didn't have physical science last year, then you might feel a little bit lost. So we're going to do a brief review here just of kind of some of this chemistry stuff. So we start with talking about like atoms. Remember that an atom is the smallest unit of matter that still retains the property of a particular element. So every element, say I have a block of gold, is made up of individual atoms of gold, and each atom of gold has the same properties as every other atom of gold. Atoms are made up of particles, subatomic particles, and the three subatomic particles we have are protons, and protons have a positive charge, so I'll write a little positive next to it. We have electrons. And electrons have a negative charge, so I'll put a little negative sign next to that one. And then we have neutrons. Neutrons are neutral, meaning they have no charge, so I'm going to put a little zero here. That zero indicating it has no charge at all. When you look at the periodic table of the elements, I'm going to put a periodic table out here for you guys to look at here. On the periodic table, you have numbers, and I don't know how well you can see it because this isn't the best camera in the world, but you'll see at the top of carbon, for example, there's a 6. At the bottom, there's a 12.0107. So those numbers indicate something special about carbon. We're going to talk about carbon because carbon is the element that's the basis of all living things. It's a very important element. It makes up the basis of all organic molecules or living molecules. So carbon, we abbreviate it with a capital letter C. That stands for carbon. And carbon has, it has 6 protons. If you remember, by looking at this here, the number here at the top of the periodic table for carbon is a 6 right there. So the atomic number for carbon is 6. Atomic number is the same as the number of protons. So carbon, its number, atomic number is 6. That indicates the number of protons. So we can put up here as a definition that the atomic number is equal to the number of protons. And so that never changes. Every time you have carbon, you talk about carbon, its atomic number is always going to be 6 because it always has 6 protons. Okay, so the atomic number here of carbon is 6. Another number we talk about is something called mass number. The mass number, this is pretty much how much the little atom weighs, that's its mass number, is equal to the number of protons plus the number of neutrons. Protons and neutrons are quite heavy, and electrons are almost without mass. They're almost massless. They're very, very small, very light. So we don't add up the electrons when we determine the mass number. We only look at protons and neutrons. So when we look at carbon, the most common type of carbon that we see is carbon that has a mass number of 12. It's very common, very readily seen mass of carbon. This means that because carbon always has an atomic number of 6, always, always, it has 6 protons and 6 neutrons. That's how we get that mass number of 12. Okay, this is pretty simple math here, right? 6 protons plus 6 neutrons. We have another word that we use, and that word is called isotope. So the isotope is kind of like it's like the version of that element. So isotope, we're going to say it's kind of like the version, or we could say breed if you think about like dogs, for example. Like there's many different kinds of dogs out there. They're all dogs, but whether you have a boxer or a Jack Russell or a golden retriever, there's different versions or different breeds of dogs. So the isotope is kind of like that. It's a different version of that element. This is determined by the number of neutrons. And I'm using the little hashtag because that usually meant number before it meant hashtag anything. Number of neutrons. Okay. So an example, we said carbon 12. Carbon 12 is one isotope. I'm going to rewrite that down here. And again, in this case, 6 protons, 6 neutrons. Then we have carbon 14. Carbon 14 is another fairly common isotope of carbon. Remember, carbon always has 6 protons. The atomic number can't change. What can change is the number of neutrons. So it has 8 neutrons in this situation. Okay, so 6 protons, 8 neutrons gives us carbon 14. Now here's another thing to look at. When we look at, so these are isotopes. What changes with an isotope is oftentimes how stable the isotope is. Carbon 12 is very, very stable. Carbon 14 isn't. It's radioactive, actually. So, that's something we see with other isotopes sometimes. So let's look at another term here. Isotope is one thing. Another one we think of is ion. An ion. Well, normally in an atom, the protons and the electrons, it's a little breezy in here, sorry. The protons and the electrons are going to be equal to each other. So with carbon, remember, has how many protons? It has 6, remember, 6 protons, 6 positives. It's going to also then have 6 electrons, 6 negatives. Remember, protons are positive, electrons are negative. When you think about how that balances out, we have 6 positives, so positive 6, plus negative 6, which means the total charge of a carbon atom is 0. It's neutral. It's not positively charged or negatively charged. The positive subatomic particles balance out the negative subatomic particles. And it doesn't matter how many neutrons we have, because if we have 6 neutrons or 8 neutrons, they're neutral. They don't have a charge of themselves. So those don't matter when we're looking at ions. Now, sometimes an atom will either give away or gain additional electrons. So giving away this makes ions. Right? If I change this number here to say 8 instead of 6, or if I take away some and change it to a 4 instead of a 6, that's going to change my total charge. That's going to make this not 0. Let me give you a real example, because this carbon doesn't kind of behave that way. But a real example is sodium. Sodium, believe it or not, has an abbreviation of Na. Sodium has 11 protons and 11 electrons. Now, typically, sodium loses an electron. It takes one of those guys. It's going to give it away to something else. That's how sodium typically behaves. So in that case, it would have a positive 11 plus a negative 10 because it's going to give away one of them. Well, when you do that math, you end up with a total of positive 1. These don't cancel completely out. When you add this problem up, you get positive 1. So sodium in general has a positive 1 charge. Sodium all by itself is neutral, but it quickly gives away that 1 electron and it becomes positively charged, and we call this a sodium ion. Now, the reason why this is important is because ions can bond with other ions. Sodium will oftentimes bond with another ion, chlorine. Just so happens that chlorine likes to take electrons, so chlorine becomes a negative 1. And when the sodium and the chlorine come together, they'll form a compound, sodium chloride, which is just salt. That's neutral now because the positive and the negative cancel out. And this is what we call an ionic compound. So we call this guy here, sodium chloride, an ionic compound. So ionic compounds occur when ions stick together. So certain substances in nature are considered to be ionic compounds. Another type of substance you'll have in nature is something called a covalent compound. And just to kind of be simple about this, I don't want to go into the chemistry of this. A covalent substance occurs when electrons are shared. So for example, water is a covalent substance, hydrogen and oxygen, H2O. So electrons here are going to be shared among like all of the different atoms that are found here. You'll find some electrons that are kind of overlapping, like the electrons of the oxygen atoms kind of overlap like a chain. Think about chains that are kind of bonded together like that. And that's how they stick together. They don't stick together because of positive and negative charges. They stick together because they're kind of linking those electrons together. The electrons will orbit more than one of the atoms. Okay, and that kind of gets us into water. Like water is super important because water, obviously you guys know water is important. You need it to stay hydrated. It's really important in chemical reactions and stuff like that. But the chemistry of water is super important too. And I have another video on the chemistry of water that you should watch to find out why water is more important. Another little thing with the review here that I want to talk about is, well, there's a couple small things here to add to this, okay? So let's say you have something you want to mix up, something you want to make in your lab or whatever. We have, I'm going to make this realistic. This is supposed to be a beaker, but not a very good drawing. We'll make it a pitcher. You're making some Kool-Aid. And it's not the kind that you have to mix sugar into it. It's the kind that actually comes already pre-mixed, right? So here's my pitcher. So I have a little container of Kool-Aid. right? And then I have water. I'm going to add the water to it from my faucet. Sure, this looks like a faucet, Miss Peachy. Sure. Oh, a little artistic. I don't know. That's supposed to be like this, the little hot and cold little thingies, spigots or whatever on the faucet. And there's your little drain plug or whatever. And there's your faucet. Okay. I think that's kind of recognizable. Or it kind of looks like a really weird animal with some crazy buggy eyes. I don't know. So we're going to get some waters coming out of this. It's supposed to be water, so you can kind of tell it's water. So those are my two ingredients, right? Once I mix it all together, I make myself a lovely pitcher of Kool-Aid because I'm so thirsty. Maybe it's like, strawberry Kool-Aid. That happens to be the color highlighter I have sitting on my desk here. So yummy strawberry Kool-Aid. This dealio here is called a solution. And the Kool-Aid, the stuff I'm mixing into it that I want to kind of dissolve, this is called a solute. And what I have to mix it with to get it to dissolve is called the solvent. Oh, I can't spell. Sorry. It's O-L-V-E-N-T. Okay. So solute is the thing you're trying to dissolve. The solvent is what you're dissolving it with. And the solution is the mixture of the two. Okay, so that was kind of talked about in your chapter as well. The other term that was talked about is something called a suspension. And this isn't when you're naughty and get kicked out of school. A suspension is if you have a mixture, but instead of completely dissolving it, there's still little things like floating in there. So I don't know if you ever try to take, you look at salad dressing, for example. Let's say I have a bottle of like Italian salad dressing. And there's like little flecks all inside of it like that. They can't dissolve, so they're just suspended in it. So it's called a suspension. Right? So that's the difference between solution and suspension. And the final thing that was discussed in this section of your chapter was pH, acids and bases. Again, this is a brief overview. So pH is a scale from 0 to 14. 0 to 7, not equal 7, right? So it's between 0 and, how do you write that, ladies and gentlemen? Is it like that, kind of? It's supposed to be my like greater than, less, whatever, less than 7, but not equal to 7. These are acids. Anything greater than 7 to 14 is a base. Only 7 is neutral. It's neither an acid or a base, okay? That's the middle guy. What does this mean? Well, sometimes water, we talked about water before, H2O. I'm going to write it as HOH. You can write H2O as HOH. Likes to split apart into the H side, which is the hydrogen ions, and the OH side, which are what we call hydroxide ions. When you have a solution that contains mostly or more H's than OH's, so it has a greater amount, an imbalance of hydrogens. So, yeah, let's just make that the solution. And I'm going to put H plus is greater than OH here. These are called acids. When you have a solution where the OH's are greater than the H's, it's called a base. So we look at the balance between hydrogens and hydroxides in solution. So H is hydrogen. I think you might know that one already. OH, it's called hydroxides. If you think about the word, it's got both a hydrogen and an oxygen, so it's hydrogen oxide, hydroxide. That's where that word comes from. So that's the difference between an acid and a base. So sometimes, in your body, it's really important to maintain a state of homeostasis. We're going to talk about homeostasis like all the time. There's literally just homeostasis and death. If you can't maintain homeostasis, you die. So it's really vital, right? If your body starts to go out of homeostasis, there are processes that put it back into homeostasis. Because if you go out of homeostasis and you just can't get back to homeostasis, the result is death, and that's not a good thing. So one of the things that helps to maintain homeostasis are these things called buffers. So buffers are weak acids or bases that basically regulate pH in the body or regulate the acid base levels in your body. Okay, so I'm going to put the definition here. These are weak acids or bases that regulate pH. So, for example, in your blood, you don't want your blood to be too acidic or too basic, or you'll go out of homeostasis and die. So there are buffers in your blood that regulate the pH of your blood, so it neither becomes too acidic or too basic. It's very important that those buffers are working properly to maintain homeostasis, right? And we'll talk more about that when you guys learn more about that kind of stuff. We talk about respiration and why your blood might not maintain its proper pH, why those buffers are necessary. But I just want to introduce the term buffers today. So remember, acids have a pH of less than 7, and that's when you have more hydrogens than you have hydroxides. Bases have a pH of greater than 7, and that's when you have more hydroxides than hydrogens. And your body needs to maintain homeostasis, so it has these buffers that change the pH basically so that it stays where it needs to be. Remember, certain parts of your body, like your stomach, have a very low pH. They're very acidic inside your stomach. You want that to stay that way. But your blood is more close to that neutral pH. So that's important to stay that way. So different parts of your body have different levels of pH that is necessary for homeostasis. So it's not the same throughout your whole body. Hopefully that was a good overview, guys, of kind of some of those chemistry type concepts, and hopefully that helps out a little bit. If you have any questions, send me an email and I'll help you. I can get back to you and maybe give you some one-on-one help. Have a great day, and we'll talk to you later.